Hey everybody, welcome to PC Perspective. I'm Ryan Shrout, joined by Tom Petersen from Nvidia. How you doing, sir?
I'm great. It's good to be out here again.
Today is May 17th. It is the release day of the reviews of the GeForce GTX 1080, Pascal's first kind of consumer GeForce part. So now we've moved past 28 nanometer. We're into the world of 16
nanometer FinFET. And what I like is that if you just kind of think about the jump we would have taken because of the process,
yep,
it's nowhere near as big as the jump we've taken because of the combination of process and architecture and a whole bunch of other stuff that I'll tell you about. So the first thing is I'm going to cover 4 big topics. Ansel is actually a new technology to do much more elaborate, much better in-game capture. So the free camera says, hey, here, if this is my in-game view where I'm playing Witcher 3, you might want to rotate the camera, zoom in, look at different effects. You're freezing time, but now you're able to kind of position your camera before you grab that perfect shot.
Right.
Now, post-processing is also supported by Ansel. All of the effects that we support are just amazing. There's halftones, there's vignettes, there's distortion, there's tone mapping. So the idea is, hey, let's let people get really creative in-game with their UI, kind of getting it to look at just exactly how you like it, and then you hit that capture button and you're good to go. Super Res, another fantastic capability. So the idea here is I want to generate a super high-res quality image so that I can then zoom in and see the minute details in that shot. Another capability of Ansel is to save what we call RAW, which is EXR capture.
Okay.
So the idea is, you could save a JPEG, but then you're kind of limited to the bit format of JPEG. By saving EXR, it's got all the raw data and it supports HDR. Lastly, as we mentioned, it is ultra high resolution, so this is 4.5 gigapixel images. Think of it as just lots of screen captures and then stitched together using CUDA, and you can generate just gigantic images. The last capability of Ansel is, of course, we can also do 360. So if you can kind of do a gigantic super res thing, you can also do it in a photosphere, and we can stitch that together so you can look at it in VR and you can share it to people and look at it with your phones. So that's Ansel. It's coming soon to games. We're integrating right now The Division, The Witness, Lawbreaker, Witcher, Paragon. And these are all titles that are just going to generate these incredible photorealistic images controlled by users. Next topic is VR. But first of all, the whole pipeline of VR is pretty complex, because anytime you fake anything in VR, you can tell right away. You can't do like a bump map anymore. It needs to be geometry. So the idea is you need great graphics because you're going to get a lot more shapes, a lot more geometry,
right,
a lot more processing. But you have the same problem with audio. The problem with audio is your head, again, since you're in this virtual world, you're going to pick up on anything fake.
Right.
And today, audio in VR is actually kind of not cutting edge, right? Multi-channel surround today is mostly directional.
Yeah.
Right? Now, the problem with that approach is your brain is easily mismatched. Now, our solution to this kind of complex problem is effectively going after directional audio. What's happening is you kind of infer where is the sound by looking at time differences in your 2 ears, right? If you have a sound source that's off to the right, you'll hear it on the right-hand side before you do on the left-hand side. And then similarly, you'll hear different levels of audio on the left and the right. And lastly, you'll hear these tiny little reflections off of different parts of your bodies. So this is the level of simulation that's required to get a good audio experience. And fortunately, that's exactly the type of simulation that's happening with our new technology called VRWorks Audio. And the general idea is very similar to ray tracing. So if you think about the problem of optics, you're going to simulate light as it bounces around, an environment.
Right.
In this case, we're actually using a very similar engine to simulate how sound is going to bounce around in an environment. So if you think about this picture, this is how most audio works today, right? It's directional. So what's going to happen is wherever your source is, you're going to do effectively a directional positional calculation. And you just kind of say it goes straight into the guy's ears.
Right.
And you might tweak it slightly to try to simulate some occlusion and stuff like that, but it's effectively a distance-oriented attenuation, right? Now, the next level of this is what we're doing with VRWorks Audio. So instead of doing just a positional simulation, we're actually doing a simulation of all the reflections. Because remember, the audio source starts and it emanates in all directions. So kind of clicks out as a wave, it bounces off of things, and eventually hits a person's ears, but you're getting all kinds of different ambient effects. And if you look at this picture, this is telling you how it's going to work. It's path traced. So effectively we simulate an emitter, right? That's the audio source, and it goes in all directions. It bounces off the sides, it bounces also off of different objects, but eventually lands on a person's ear. And all this is being simulated in real time. graphics is all about creating these incredible visual models, right? And you got to be able to run a lot of frames per second. So we've invented 3 new technologies. This is a view of what is happening with displays, right? So we started off flat, where effectively everybody has one monitor that you're interfacing with, but we already know people have started ganging these things together, and now there's 3 monitor configurations that are being used. There's also curved monitors, like
we have several of those here.
G-Sync ones that have come out, and there's some non-G-Sync ones. But the idea is that you can get more immersive, higher quality experiences by beginning to put yourself inside of the monitor. And of course, VR, AR, and finally, in the long run, you'd love to see a hologram. Now, what's a hologram?
How long till you bring one of those?
Well, let's think about what a hologram is. It's the same object, and the way you're able to perceive a hologram is because it's being reprojected as you change your orientation. Okay, it's really complicated, I know, but suffice it to say that displays are changing, and it's all about projection. Because all of these displays are in effect providing different projections into a 3-dimensional world. That's why we have simultaneous multi-projection. What it allows us to do is build arbitrary projections in real time with 0 performance impact.
Okay.
And that allows us to match all these different displays. But it's impossible to understand it unless I show you a demo. So what this is, before I begin, I want everybody to know this is an artist rendition, right? We're showing you a spectator, and the spectator is, where I am, it's my camera position, but we're looking at what is really how a computer game works. And the way a computer game works is there's these models out here in 3-dimensional space, the sphere, the pyramid, the square. A game is developed by first creating models, and then the models are positioned in this 3-dimensional space, right? All of that work happens completely independent of the viewport. If you look at, as an example, if I move this view around, you can see that all the work that is happening to create that 3-dimensional model hasn't changed, right? It's totally orthogonal and independent of the view. Now, the last stage in our geometry pipeline is translating. We're going to have to translate from this 3-dimensional model to your screen. And it's that translation process that's called projection. And if I kind of try to explain what projection is, let me come down and kind of get over the head of this guy. So imagine that you're sitting right at that center dot, right? If you're sitting there and you're looking around the world, let's go ahead and look around the world. You're looking through a window into that 3-dimensional world, and projection is the art of converting all the math and making a 2-dimensional array that we can then raster. The key thing is, this used to work really well, and there was sort of fixed functions that did this projection in hardware, and it never needed to change. But what's changing is now people are using multiple displays, okay? So let me show you what a multiple display looks like. This is a Surround as an example. So with Surround, people have now organized their displays in these long, flat projections. So let's say what happens when a gamer creates this image, they normally rotate their monitors, and when you do that rotation, you get something like this, right? The game does not know that you've pulled your monitors in. So by pulling them in, you actually make this distortion even worse. And if you think about looking around as an example here, you can kind of see how it's really stretched out on the sides. That's the experience that gamers are getting today with surround configurations. And it obviously gets even worse with wider FOV.
Yeah.
Okay? Okay. So now the solution to all this is called simultaneous multi-projection.
Right.
What simultaneous multi-projection does is, instead of kind of having a fixed relationship, a flat viewport, what we're actually able to do is chop up the projections into multiple sections and then adjust those to effectively tilt them in the projection space. The multi-projection is exactly correct, like you had separate cameras. So that's effectively how we implement simultaneous multi-projection and how it applies to our first use case, which is surround. Now we're providing a UI and APIs for game developers to make this easy to implement. So if you're doing a big multiplayer world and people are already using surround monitors, we're making the alignment and adjustment of this experience very straightforward. So now we're going to go to the next one, which is a little bit more complicated, which is virtual reality. Okay, so now the first thing with VR I want to talk about is effectively there are 2 views. you have a left eye. Let me come spin around. So you have a left eye and a right eye. The view is different because your head has two eyes that are positioned in different locations.
Wait, really?
Yeah. So when you look at stuff, it's different. Now remember how we talked about how this works today?
Yep.
How does it work today? Quick quiz.
You render one geometry pass completely, and then you render a second one completely as well.
You basically take two passes through the entire pipeline,
Yep.
all the geometry. In this case, it gets even faster because you can actually do what we call single pass stereo. And single pass stereo says create the world once and then project it to your left eye, project it to your right eye without recreating that world. So that's the first thing. Simultaneous, or it's called single pass stereo. Now the second thing that's happening, and most of you guys are about to freak out, is there's a lens. The big picture in the back, the one that's the first square, kind of the larger square, that represents what's on their headset. Now your retina is represented by the smaller square.
Okay.
And so the lens is just an optical aid to help you remember there's a lens there. So what you can see right away is that there is in fact distortion happening in your retina. And if you look at those boxes, they're getting bent out. And the question is, why is that happening? Well, because the lens is there to focus the light that's on the screen at a very short distance to the back of your eye.
Okay.
And that unfortunately causes distortion when it does that. So this big grid over here, the one on the outside, that's the area that was originally shaded. And then we ran another shader program to effectively compress it. And that's sad because those pixels are perfectly good, but the reason you compress it is to get a square image out the back. And the better way to do this is with SMP. Let me show you what that looks like, okay? So what's happening here again is if I warp it, what we're doing is creating a projection that matches the shape of the lens. Okay, so again, this is using our SMP technology, and we call it lens match shading. And what we're doing is we're chopping up the viewport, chopping up the original projection into 4 slices. Each slice is kind of transformed and tilted to match the shape of the lens. And so the cool part about it is now the actual image that we're rendering looks like what we need it to look like for VR. So the original surface, the original rendered shape is kind of roughly, let me turn off the warp. That's the original way.
Okay.
We would render the big square, and then we would throw those pixels away and compress it down to this sort of barrel shape in the background. The new way to do it, using SMP, is instead of doing all that extra work, you actually render it directly at the reduced pixel size. So that shape that you're looking at there, if I kind of come back here and kind of go down a little bit, whoops, go down a little bit, and that is all pixel savings. Right, the reduction,
all the border
that you're not seeing.
So simultaneous multi-projection is basically a functional section of the geometry portion of the architecture.
Think of it as very close to the bottom of the geometry pipeline. If you think about how do GPUs work, they do effectively creation of objects, and then they do geometry processing. All of this, it's creating that world. Remember that picture I showed you where there's like a 3-dimensional geometry? That's what the front half of this pipeline does.
Okay.
And then the very last thing that happens is projection into these multiple viewports. And of course that feeds into our raster setup, which does things like clipping and other stuff like that. And finally, all of those primitives are used by the shader, by the pixel shader, and you're kind of sampling into that space to create the final dot that's on the screen. So the way we've described it is it's our Polymorph Engine 4.0, and one of the blocks in the Polymorph Engine 4.0 is the simultaneous multi-projection block. Now that means when you add all those technologies on top of the fact that Pascal is just a faster part in general, we're really dramatically faster. We're 2 times the performance of a Titan X and 3 times the efficiency versus a Titan X.
So let's get into the actual product that people want to know about.
Yes, GTX 1080. So there are actually 5 things that we've done with GTX 1080 that are pretty amazing. First, of course, is architecture.
So, I mean, if people have read reviews or seen the launch from last week, we know most of these specs. 1.6 gigahertz base clock, 1.73 gigahertz boost.
Yep, and 2 gigahertz overclocking. Now, base clock is our clock when we're under thermal stress. So it's the clock that we say, if you do everything crazy, unless you really like put a sock in the fan and you kind of stick it in an oven, this is the lowest clock you're going to get. 1.73 boost clock means that's your typical clock. Running a typical application, running in a typical environment, this is what everybody should expect to see. And then even before you overclock, you're going to run normally higher than 1.73. And then when you're tweaking it and you're overclocking, we're going to see a lot of people greater than 2 gigahertz. The number we showed at the Editor's Day and at the main event is certainly the fastest ever observed on air, and it's almost the fastest as ever observed on liquid nitrogen. Yeah, it's crazy.
That's pretty impressive.
Yeah, very, very fast. Now, the memory is a big part of what makes Pascal crazy good, right? We've redone entirely the memory interface. There's a new architecture, a new microarchitecture. Of course, we've also got a brand new board design. So the point is that just getting this interface so well constructed is a major accomplishment. And that results in 10 gigahertz transfer, which is really, really, really fast. Now, we've also improved memory compression. So memory is a very rare and scarce resource, memory bandwidth.
Yeah.
So by improving our compression, we can take more advantage of that interface. Now, of course, this is completely lossless.
Right.
So when we can, you look at kind of adjacent bits in the frame buffer and you say, that's the same value. So if it's the same value, instead of writing the value twice, we kind of write the value once. And then imagine that we can do that for patterns of 4. So if you look for 4 that are matching, write the patterns of 4 into the frame buffer once. And now with Pascal, we actually can do 8 to 1, and we can do combinations of all of them. So 8 to 1 says, hey, you get 8 bits in a row, just write it once. Remember, it's an 8 to 1 compression. And of course, you can also write uncompressed.
Right, which actually, it's fully utilizing your throughput, but you would like to be able to compress it so it gives you a higher effective
Yeah, the
bandwidth.
idea is there's a lot of locality of space in the frame buffer because you're looking at images that have similar color. Now let's go on to the next slide and take a look at an example. So this is Project Cars,
right.
But there's a lot of detail here that is in fact the same color. So this is what Maxwell would have done. You know, Maxwell had compression as well, and the magenta represents bits that would have been compressed, okay? You can see we picked up a lot of the scene, but like the green stuff just didn't have it. It was very close, but not exactly the same on the green stuff.
Right.
Now with Pascal, we're actually able to do much more compression. We pick up much more of the bits. And so this is the result. So we started off with looking at 980 versus 1080. Right away, we're 40% faster just because it's a faster interface. But we're adding compression benefits, moving to the next generation compression. And so our total effective bandwidth is 1.7 times what it was on 980. So it's truly a gigantic upgrade in the memory interface. Also, HDR is coming. It's the biggest change to monitors in 20 years. I would say one of the biggest changes.
I'm a little biased.
Yeah. One of the biggest changes. This represents every color that your eye can see. The triangle says, my display can show you some blue, and it can show you some green, can show you some red, but it can't show every red that's possible. So these colors you normally don't see on displays. HDR is increasing from the little triangle to the big triangle. So we are doing HDR gaming, of course, so working with game developers to implement HDR. We also support HDR video, 4K at 60 with HEVC decode, which is H.265.
Yep.
And we do decode and encode. And of course, we have all the right interfaces. This should actually say, I believe, DP 1.4 ready. But we expect that when we can be certified for DP 1.4, that Pascal will be certified for DP 1.4 as far as we know. And also HDMI 2.0B is again HDR. Another cool thing is HDR TVs are here already. We're also doing game stream. So the earliest way to get gaming on an HDR TV is to do game stream. You take an HDR game, run it on Pascal, then it's going to stream it across your network to Shield, which is the best way to connect to a TV. Everybody knows that. And now Shield obviously has an HDR encoder built in, or decoder built in, which will connect through HDMI 2.0B to your HDR TV. So this technology is coming very, very soon. Yeah, very cool. Also, we're working obviously with game developers all over the world. So HDR is the next big thing, and NVIDIA's all over it. So first I want to talk about fast sync.
It should be quick.
Fast sync should be quick, right? The big news is that here's game engines, right? Game engines, or the game pipeline, is a game engine doing its thing. It sends frames to DirectX in our driver. The driver then manipulates the GPU, and we're going to render. We're going to stick it into a buffer, and finally we're going to display it. What we've done is effectively made this better. So today you have two not awesome choices. When you have a high frame rate game like Counter-Strike or almost anything running on Pascal, you have two choices, VSync on or VSync off, right?
Right.
VSync on means you're going to get back pressure. VSync off means no back pressure. But what happens when you get back pressure? Everybody knows that VSync on has high latency. And it has high latency because you're slowing the game engine down effectively to 60 hertz, and that 60 hertz has to kind of bubble forward through the pipeline because the game engine is running at 60 hertz now. So since the game engine is running at 60 hertz, you're only going to get 60 updates of anything per second. Now the other option, people hate this, especially competitive gamers, so they turn VSync off, and you get very low latency because effectively that pipeline is running very, very fast, and every stage goes very, very quickly. The problem is you get tearing because you're not synchronized to your monitor anymore. So what we've done is we've changed this pretty fundamentally. And what we're doing is we're decoupling the render and display. Okay, what decoupling render and display means is this front end can run independent of what's happening on the back end. And rendered frames can now live in a queue for largely an indeterminate amount of time, and then we'll pick when we display it. So that allows us to run the front end very fast while still manipulating the back end however we want. So the decoupled render and display, what it actually allows the game engine to do is run very, very fast, and it's going to stick the data into the back buffer, which is where you're rendering into. All I've done is basically chopped up that thing that used to be one buffer, and now we're going to call it front buffer, back buffer, and a new thing called a last rendered buffer. Okay, so the way this works is games are rendering into the back buffer. When the back buffer is completed, all I'm going to do is I'm going to flip the names here, and effectively the back buffer becomes the last rendered buffer, and the last rendered buffer becomes the new back buffer. And that's going to continue forever until we finish scanning. Once we hit the bottom, we're going to do some renaming again. The front buffer is now going to point to the last rendered buffer, and the front buffer becomes the next back buffer. Okay, so think of it as going back and forth while this is scanning. Once we get to the bottom of the scan, we say, okay, what's the last rendered buffer? The front buffer then points to the last rendered buffer, and we start ping-ponging here. All the while, the game engine knows none of this is going on. What that gets you is fast sync. And it's a new option in our NVIDIA control panel. When you get a Pascal, you'll see it as a drop-down. And what it allows you to do is say, I don't want any flow control. So just like VSync off, the flow control is gone. However, in this case, you have latency very, very similar to VSync off. So somewhere between 8 and 15 milliseconds more latency. But that's way, way, way less than VSync on. But at the end of the day, there's no tearing, just like VSync on case. All right, so this is some data. I think this is CSGO. And you can see with VSync on, you get around 90, a little bit higher than 90 milliseconds. These are different samples using a high-speed camera. And you can see VSync off and fast sync are very, very similar. But again, the benefit of fast sync is you get no tearing, just like VSync on. And it really does give you a great experience. SLI update. So first of all, let me show you this. There is a new bridge. It's called the SLI HP bridge.
High bandwidth.
High bandwidth bridge. It's actually double the bandwidth of the prior bridge, and even more than that because we're running at a higher frequency. So the first thing with Pascal is our interface on Pascal obviously is faster than it was on Maxwell. So when we have properly tuned bridges, like the high-speed bridges, we can run that interface at 650 megahertz. Prior bridges that were the old SLI kind of floppy cables and even rigid cables before LED days, those were not as well designed for high frequency because all of our GPUs were slower. Now we can detect those bridges and we'll automatically configure it correctly. Now what can you do with the bridge? Well, the bridge actually connects two GPUs together, so both of those MIOs, we call the interface MIOs, those are directly connected for two GPUs. So before there were two because you could do more than two GPUs and you would connect these up in interesting topologies. Now they are both connected directly to each other and we're doing two GPUs. So what you can do with this new bridge is all about higher configurations of displays. So what's happened is our standard bridge is sort of run out of bandwidth at a single display running at 25 by 14 and 60 hertz. This is roughly the limit that we can support on our older bridges with Maxwell. Now with our high bandwidth bridge, we can actually support 25 by 14 at 120 hertz up. We can support 4K, we can support 5K, and we can support surround. So all of these configurations work obviously on Maxwell. But what we're able to do with Pascal is run those natively over the bridge. Before, we didn't have enough bandwidth on the bridge, so some of these transactions would run through PCI Express. There's a lot of contention on PCI Express, and it's a little less assured interface. With our bridge, this is as if literally we're scanning out of a remote frame buffer and putting it on the pixels going to the screen. So that's why there's a bridge. And the reason the bridge got higher bandwidth is because of new monitor topologies, including surround. Our multi-GPU support is changing with Pascal. So at this point, it's time for NVIDIA to start leading a little bit on this topic. So the first step is education. There are, in fact, now 3 modes that Windows is exposing for multi-GPU on DX12. Okay. The first one is called multi-display adapter mode. It can be any vendor, it can be any color, it can be any shape GPU. It's just an adapter. And each adapter is completely logically separated from every other adapter. The way to think about that is the application is now responsible for any kind of multi-GPU architecture. From a driver's perspective, you can break it down into pieces. There's something called an adapter, which is a Microsoft term that says, tell the app how many adapters there are. So in MDA mode, however many GPUs there are, that's how many the app sees. It'll say adapter 1 is this, adapter 2 is this, adapter 3 is this, and the driver has done nothing, right? Now, there's another level of abstraction beneath adapter called a node. So with multi-display adapter, there's one node per GPU, okay? Nodes per adapter, there's one. And effectively, again, the MDA mode means it's just one GPU.
So there's one node per adapter, but you could have multiple adapters based on the number. Okay.
Yeah.
If the game said you can use 4 GTX 1080s,
go for it.
Then boom, install 4 GTX 1080s.
Absolutely. So this is the column that some developers are going to use going forward. Now there's another mode called Link Display Adapter mode. Now Link Display Adapter mode unfortunately has 2 sub-modes, okay?
So LDA is Linked Display Adapter.
Yes, linked, and it's called Link Display Adapter because the 2 display adapters are in some sense connected together.
I see. So that no matter what you had, if you have 2 1080s, they show up as one adapter. They report back as one adapter to Microsoft.
And so the driver is responsible for doing anything underneath that hierarchy of abstraction. Okay. In this mode, there's one node and one adapter, and the NVIDIA driver does everything. We call that SLI. Now what's changing, and I want to be straightforward about it, is right now NVIDIA is saying 2 GPUs are going to be our focus going forward for Pascal in this mode. And as a matter of fact, we're going to make it so that end users can still configure for 3 or 4 if they really want to, if you're doing benchmarking, if you're enthusiast.
You have to go register yourself with an NVIDIA website. You download a piece of software. The software actually updates the firmware of your cards. And then it allows 3 and 4-way to work. What's the purpose of that process?
What we're trying to do is generally communicate to everybody that, hey, there's a real thing here. I would love to sell GPUs because we love and we want people to enjoy it. And there's no reason why Pascal couldn't support it. All the hardware works, and the reason it's not just on out of the box is because what we're trying to communicate to the market is if you think it's just going to be beautiful all the time, you're mistaken. Okay, the third column is really similar to the first column. It allows the application to leverage some of the resources that are available if the GPUs match. So this is actually what we are recommending game developers do if you're going to do an explicit SLI kind of architecture. Okay, so GPU Boost 3. The general idea for GPU Boost is there's a frequency curve, right? And you're moving up and down between voltage and frequency and dynamically based on things like temperature and power and a whole bunch of stuff. We're going to pick exactly the instantaneous frequency peak. Another thing about GPU Boost 2 is it had a fixed frequency offset. And what that does is it moves the entire curve by the same amount. Now the problem is somewhere out there is this theoretical max clock curve. So every GPU has a different curve. It's based on your silicon. And the idea would be if we could discover this to run at it. But we know that this fixed offset is less good because effectively this shape of the curve is not linear. What we're doing with GPU Boost 3 is we're going to recover some of this lost opportunity by allowing the frequency offset to be variable per voltage point. What it means is that users can effectively create their own voltage frequency curve per GPU. So this is a new version of Precision that we've been working with. It implements GPU Boost 3, and it's got the power target, temp target, and the GPU clock offset. So if you slide this GPU clock offset, you're kind of doing what you've ever done. It's just like GPU Boost. You can slide it around, and you can hit apply, and all of a sudden you're going to be running faster. So let me go ahead and turn on a benchmark here. All right, so I added just off the top 122 megahertz. I just picked that number randomly, of course. And you can see in our real-time display here on the main picture, right now it's running at 1987, kind of coming up and down. I've added 122 megahertz to the clock, and I'm sure I can go higher. So this is a very typical experience. The temperature right now is ramping up to 62. Our temperature target, you can see, is 83C. So it's going to get to 83 and then it's going to stabilize, right? Okay, so on Precision, you've got these two big yellow buttons, and that is your menu system. And right away, you'll see we've come to a brand new page. Now, the blue here is showing your specific voltage frequency curve for the part that we're looking at right now. The green represents the overclock that you've currently got. So
that's our plus 122.
That is our plus 122. And we're in what's called basic mode right now, which effectively says there's a fixed relationship, a fixed offset applied across the whole VF curve. And you can see I can raise and lower my entire VF curve by just kind of moving around. So I'm going to say, okay, 100, that's 200 megahertz. And then I hit apply. And right away, I'm now at 2050 or 2025, and I've upped my overclocking just by clicking on the little basic curve. So what's happening in real time is we're moving up and down this curve that we've created.
Right.
Now, that's only one mode. As I mentioned, you can now get more sophisticated. So linear mode allows you to have one point at the bottom, let's call it here, and you can have a higher point at the top.
That seems like the wrong way to do it,
That seems backwards, right? So what you might do is low at the top and high at the bottom. But you know, the truth is, you might not want to fart around with these VF curves. So what we've also built into GPU Boost 3 is the ability to have a scanner. Now in manual mode, you can obviously click around on the grid. Now let's just click one here. And you're actually entering your own VF curve. What the scanner's going to do is start at the bottom of your voltage frequency curve. It's going to run a test. In this case, it's running sort of the Fermat donut. And then it's going to test between 100 and 200 megahertz and for 2 seconds. And it's going to run a series of tests, and it'll create your voltage frequency curve for you. So we got the EVJ thing running.
So you see, it's basically it's running a test looking for either visual corruption or the driver to crash, right? And it runs it for 2 seconds. Ideally, you want to do this longer so you have a more stable system. You're getting an accurate thing. But for our purposes, we're just kind of speeding things along. You can see the green bars.
The little green dots.
It will go up every, there it goes.
It goes up about every 2 seconds.
It'll go up, and then when it gets to a point where, hey, I think we're at a spot where we should stop, it moves on to the next one.
Yeah, the idea is it's doing comparisons in memory, looking for corruption, because it knows kind of the pattern that
you have a reference of what it should look like.
This is what it should like when I'm all done. So if it's not looking like that right this second, you can capture per pixel errors, right? So you can imagine running this overnight, running it very exhaustively, and you'll get effectively a custom voltage frequency curve for your part.
Right.
And then when you're all done, I'm just going to cancel this now. When you're all done, you just click apply, and then all of a sudden you're running at that new scan frequency. Okay, so that is Precision in a nutshell, and it's a GPU Boost 3 in a nutshell. Over here is your overvoltaging. We've actually made that easier to use. It now goes between 0 and 100%. Again, one of the NVIDIA things is we don't recommend people over voltage beyond a certain amount. But if people want to, you know, it's gamers. We do crazy stuff. So at the end of the day, over voltaging is going to be a warning, but everything else is going to be safe as it can be. You can't hurt your GPU. So that's GTX 1080, and let me show you a little bit more data. So it's 9 teraflops, 8 gigabytes of GDDR5X. It's $599 MSRP and $699 for the Founders Edition. Those will be the first versions available. And then May 27th is the general e-tail availability. And then, of course, we also talked about 1070, which is going to be available in the channel on June 10th. And $379 MSRP and $449 Founders Edition.
You ready to get into questions?
Let's do questions.
All right, so 2 big ones right out of the gate. You ready?
Yeah, bring it.
What the hell is the Founders Edition, and why did you do it?
So the way I think about the Founders Edition is it's a really good implementation of a graphics card for GTX 1080. It's with really high quality components. It's got higher quality power supplies than what we've done in the past. And it's intended to be a GPU that is in the market for a very long time. There's going to be designs that are done by AICs that are less high quality, less expensive, and there's going to be designs that are done by ACs that are higher quality, right? So the way I think about Founders Edition is it's literally, because of the quality, it's right in the middle of the stack, and that's where the price is.
My concerns with it are, I don't think fundamentally anybody has a problem with NVIDIA creating their own part that's going to be out there for a long time at whatever price point they want.
Of course.
As long as there are options at that MSRP.
Yeah, and honestly, if there's a way for us to make those go faster, we would. But at the end of the day, the AICs, our partners, are going to do their own schedules to get their devices into the market as soon as they possibly can. And they're going to be really, really close to the same timing as the Founders Edition, slightly after.
Asynchronous compute. AMD's touted up async compute at this kind of level. They talked poorly about Maxwell's implementation of asynchronous compute. So what has changed with Maxwell, and like where does NVIDIA stand on it now?
There is hardware support for asynchronous compute in Pascal, right? And it does do a better job than Maxwell, primarily around preemption. I will tell you though that async compute is just one technique of many performance improving techniques. And the benefit of async compute is directly related to, game architectures and driver architectures and chip architectures.
Right.
So from my perspective, I think we're at the very, very, very beginning of async compute. And as game developers learn more about it and we learn more about it, I think implementations are going to improve. Right now, it's really hard just to even test. And so
I found that trying to figure out ways to test it, because Hitman has asynchronous compute in it, I'm told, right? Well, if you look at the benchmarks, Pascal is very, very fast at Hitman. So could it be faster maybe, or would it be slower without async? I don't know for sure yet.
Let me just tell you, it doesn't matter, because at the end of the day, what we care about is performance.
It doesn't matter how you get to the performance necessarily, as long as you get to it and it's stable, smooth and reliable. We need to calibrate your surround displays and the warp correction to account for varying view angles with SMP.
Yes. What we're doing is adjusting the projection to exactly match the tilt of your monitor, right? So that will be implemented in a new interface provided by NVIDIA Control Panel, and effectively think of it as a training grid that you can apply, and all that information is saved inside of the control panel and then provided to games.
Why didn't the 1080 use high bandwidth memory or HBM2?
Ooh, that's a good question. If we're able to deliver the performance that we want for a more mature technology, G5X is actually more mature relative to HBM. So the reason it's not HBM is because we can deliver the experience that we want and the performance levels we want at a much more reasonable cost point with much higher availability.
With VR providing more people with 3D capable displays, is there any chance 3D vision support becomes resurrected?
SMP would be directly applicable to 3D vision. We would be able to do simultaneous stereo the same way we do for VR. Now, whether or not that means we're going to resurrect or reinvest in 3D vision is kind of an open question, but right now there's not a lot of market demand for 3D vision type experience.
Are you going to support adaptive sync?
Now, our response is unchanged on adaptive sync. Our policy right now is we're going to invest in G-Sync. Adaptive sync is a little bit more hands-off, and it's very hard for us to guarantee a fantastic experience if we're not deeply engaged on each design.
Somebody in here asked about the difference of G-Sync and fast sync.
So what G-Sync does is it synchronizes the monitor refresh with the render rate of the game. So when the render rate is below the monitor refresh rate is when G-Sync really kicks in, right? That's when, hey, I'm running at 45 frames per second or maybe 50 frames a second. I want that monitor to be right in sync to get rid of any visual artifacts caused by synchronization. Now, as the render rate gets much higher than the maximum refresh rate, G-Sync starts looking more like a traditional monitor. So that's when fast sync is going to be most applicable. When you're running 200, 300, 350 frames a second, then fast sync really shines, because you're effectively subsampling the frames and then you're mapping those to a fixed refresh monitor. The way I think about it, when your frame rate is low, then you're basically, when fast sync is on, it's very similar to V-Sync. If you're just above it, the problem is that fast sync doesn't know you're just above it.
Right.
So what's happening is it's going to sample and it's not going to back pressure.
Right.
And your experience actually probably would have been better had you back pressure, even though your latency is going to be higher. Right. So we recommend fast sync for games that are running multiple times the refresh rate. I think 2 to 3x is sort of the min. And of course, with most of these first-person shooters, you are running many more times that. All of this is in the NVIDIA control panel. It's now in the vertical synchronization tab, and you'll see under that vertical synchronization tab, you'll see on for VSync on, off for VSync off, adaptive, remember adaptive VSync, there's adaptive half refresh, and now there's our brand new baby fast.
How soon can we expect G-Sync displays to support higher reses like the DP 1.3 or 1.4 support, like 4K 120?
Wow, I would like that to be as soon as possible. Over time, obviously we're going to be improving our technologies, and that's definitely an interesting area.
Will there be support for mixed resolution surround?
Mixed resolution surround is a great idea. SMP could support arbitrary resolution surround. and you could create a projection for each monitor perfectly. What's left to be done is how would you configure such a beast, and then how would you communicate that configuration to a game developer that needs to be aware of all of this different stuff.
Right.
So it's non-trivial task, and I'm not promising that it's going to get done, but it's a great idea, and I'd like to support it.
All right, everybody. Thank you very much. Make sure you check out our review. It's at PCPer.com if you want to read more about. If this wasn't enough content on GTX 1080 for you, we have our own video review, and we actually have our full written review. I think it ended up being over like 12 or 13,000 words. So there's a lot of stuff to digest in there.
Oh my god.
So that's at PCPer.com. If you go to PCPer.com/subscribe, by the way, you can sign up for our kind of notification list where we send you notes when we're going to do live streams like this. So if you're interested in this type of stuff and you want to make sure you're here for the next visit from Tom or whoever else from anybody, any place else may show up, then go there and do that. So we will see you next time, everybody. Thanks.
See you guys.